Yeah, if you can bring your mouse over here to the whiteboard. Do you have a mouse?
I'm actually on my phone right now.
Okay. How about you, James Oliver? Do you have a mouse? Anybody have a mouse that they can bring over to the whiteboard? There we go. Okay, there's all the mice. All right, good. All right, we're all here. Hooray, hooray, hooray. Okay, so I'm going to, hey, don't draw yet. I'm going to give you guys opportunities to, or I'm going to give James Oliver. James, you're going to draw us a orbital diagram specifically for iron. All right, the iron atom. Okay. I'll start you off by giving you a line. Let's see here. I got to go over to the hand. We got to make it into a pencil for ourselves. So here, I'll give you a line. Whoops, that was horrible. Let's try that again. There we go. Kind of good. All right. And what are our units here for this line? Do you guys remember?
Energy?
That's right. This is energy. That's right. We're going to be plotting energy and getting our orbital diagrams. Now, let's see. I don't know how to erase, but I can use, I think, coloring in white will do the same thing. Let me choose my color here. And I'll try to erase whosever idea that was. That was a bad idea. Okay, so James Oliver, why don't you show us the energy diagram for iron. Start off nice and low there, down about here, so that there's plenty of room. Okay, so our orbital diagram, what's the lowest one down here, the lowest orbital? One S. Is that an S? Very good. And then we draw a little line like this. There we go. 1S. Very good. All right. What's after 1S? 2S. Very good. And a little line. Okay. Let's see. The other James is there. James, what's next? Other James. James Wiley. Wiles.
Willis.
Willis. Sorry.
Yeah, 2P.
2P. Okay. Draw us a 2P then. And while he's doing that, Katie, or no, Catherine's next. Catherine, do you want to draw what's after the 2P? 3S, very good, with our little line to represent our orbital. James Willis is writing 2 or 3 lines for the 2P. All right, so now he's wishing he would have centralized the 2P a little bit better, but that's all right.
Yeah.
Okay, so Katie Thomas, are you out there? I see Nikki. Nikki, why don't you draw what's after 3S? All right, it's 3P, good. And how many orbitals are in the 3P? How many lines do we draw above the 3P? 3, very good. Now, I don't know if you guys have a periodic table in front of you, but we have to look and see what's after the 3P. What's after 3P? Or maybe you already know. Landon, do you want to write in there what's next after the 3P? What's next above 3P?
Wouldn't it be 4S?
That's right. 4S. 4S. Now, how did he know it was 4S and not 3D? Katie Thomas, do you know that answer? How did he know it was 4S next and not 3D?
Well, if you look at the periodic table, you have to go like through that line before you can hit iron. So
that's right. That's right. And so that's how we know the order of our orbitals along here, right? Katie Thomas, are you there? Do you want to, can you draw that for us, our 4D? Sorry, our 3D? Okay. So we use the periodic table to regenerate this beautiful, I mean, that's just a work of art right there, right? We use our periodic table to regenerate this orbital diagram. And the information in this orbital diagram, it tells us how elements would like to stabilize themselves when they do chemistry, right? So last time we were talking about iron, the electron configuration for iron. Let's see, Samantha, do you want to, you can try to write right there where you're at, the electron configuration for iron. So if we write F, very good. E, so this is now turning into an art class almost, right? What do you call that? A computer art class. All right, what do we got for our noble gas core previous to iron? What is it? Let's see, whose turn is it? Landon, did you already answer a question? Oh, yeah, Malia, what's the noble gas core? Oh, she drew it for us. Argon, right? Very good. Good. And then, what's next? Malia, do you want to write the next one? What's next? And then, let's see, Samantha, Nikki got to do one. Stratton, are you around? Do you have a mouse up there? Taiwan, why don't you write the next after 4s2? You want to add that on, Kim? After 4s2, what comes next if we're trying to get to iron? What would it be? You got it, Kim? You want to write it in here? What goes next after 4s2? Better hurry. James Willis is going to beat you. He's writing it in. Oh, that's fine. So the answer is 3D. And how many Ds? How many if we're going to iron? 5? Is that for iron? I think there's 6. Right? If we count across there, 1, 2, 3, 4, 5, 6. Very good. 3d6. Excellent. So, if we go putting in some arrows on our orbital diagram here to fill that up, Katie, why don't you fill up the noble gas or argon core? And you don't need to use arrows for the noble gas core. You can just use lines to make it easier on you. Argon.
You want me to fill it up in the diagram?
Yeah. Go ahead and fill up the diagram. In fact, why don't you change colors and use a nice color that'll contrast with the red. Here it goes. Let's see what she chose. Ooh, good. All right. So there's one. Oh, I can clearly see they have different m sub s values. Positive 1/2, negative 1/2. Very good. She's following Hund's rule, filling each one once and then going and filling the second ones. Good. All right. So if we were to stop there, that's 10 electrons. That would be neon, right? So keep going. We got to fill all the way up to argon. Okay, and then Stratton, why don't you start filling in? Go ahead and finish up, Katie. Finish up the 3p. We got to go all the way to 3p, 6 in the 3p to fill up the argon. Stratton, why don't you do the rest? There's our noble gas core of argon. Are you around, Stratton? How about Samantha? Why don't you do that, Samantha? Fill up the rest there. Okay, so we got 4s. Very good. 2. And then 3D, how many? 1, 2, 3, 4, 5, and then 6. Very good. Now, from this information, Nikki, how many, well, I guess we didn't need this to answer this question, but how many valence electrons does an atom of iron have, Nikki?
It has 2.
Yeah, just 2, right? And that's known by the number of electrons that have the highest n value, right?
Yeah.
So let me try to erase this extra. It was nice, but probably not necessary. All right. So the 2 there tells us how many valence electrons, or the 4 tells us how many valence electrons, or 4 and the 2, right? Okay, so our picture is so beautiful, but let's now predict the ions that iron would form, right? I think we already know, we've already talked about it, but it's a good review for us. What ions is iron going to form? Let's see, Landon, want to help us out there? Why don't you get a white pen and erase the electrons that are going to disappear first. You might need to get a little bit thicker drawing thickness so that you can do a good erase job. But erase for us the 2 electrons that are going to disappear first when we form our iron ion. Which electrons are going to go first? Do you know, Landon?
Yeah, when we form iron.
Yeah, if we form the iron ion, which 2 electrons are we going to lose first? That's right, we're going to lose our 2 4s's because those are our valence electrons. Very good. So if this is now the, whoops, that's too big of a 2. But if we want to write the electron configuration for the iron ion, then we have in here our argon, and we would have what left over? 3d6, right? Okay, so Katie, what do you think is the next ion that would be resulting? What electron would we get rid of? Right there, that's right. We get rid of that electron, leaving us with a 3d5. Okay, very good. So, again, the value of all this is, so I'm going to get rid of make that a 3d5. The value of all this is that we can kind of make a prediction. Now, our predictions aren't always right. There's some reasons sometimes they're not right, but we have a tool here to predict now what our, how our atoms will stabilize themselves, right? Specifically, the atoms that are kind of hard to think about in terms of how they're going to be, how they're going to be stabilizing themselves are the, I need to get out my picture of the periodic table here. Oh, I don't have one. Let me show you this periodic table here. Let me get a periodic table here that I can show you. This is specifically helpful for our electrons, or our elements in this range, right? Because, and in this range down here, and even these ones down here, right? Can you see my board okay? The periodic table, people? Can you guys see that? Okay, good. So, in the past, we would just basically say anything in this region had the chance of having multiple ion or multiple charge states, multiple oxidation states. And that's it. We would just leave it at that. But now we kind of have a tool using our electron configuration and our orbital diagram. We have a tool that can predict what our how our ion is going to stabilize itself. Okay? So, let's move along here. Let's do one more. I'm going to send you guys into a breakout group because we need to have an experience where we work on an element way down here, like thallium. Okay? So what I'm going to do is I'm going to break us into groups, and what I want you to do is write the electron configuration for thallium, all right, and then identify the number of, just like we did, number of valence electrons, look at the orbital diagram, and kind of make a prediction about the kinds of ions that thallium would like to form. Okay, so let me break us up into groups here. That looks good. So, thallium, TL, thallium's the one, and we're looking for, again, the electron configuration. We're looking for, looking at the orbital diagram to predict what kind of ions it's going to form, and also the number of valence electrons, which you guys should be pretty good at. Okay, let's go to those groups.
Use the noble gas abbreviation count.
Yes, the noble gas electron abbreviation.
I think we should use xenon.
Yeah.
And then we have 6. So it's 6s2.
Yeah. Then do we have to go through like part of the F block?
Katie, can you write it for us? Can you draw it for us?
Yeah. Oh, still annoying. It won't let me change my color. Not sure why.
It won't let
there
you.
we go.
Okay.
Yeah, what match is still in the mouse?
Why is it so hard?
All right.
And it works.
Wow, you're really good at this. You might need a thinner thing, though. We're going to run out of space.
Let me make it a little bit smaller.
Okay, xenon core.
6s2.
Very good.
And then there's the 57 to 71 elements.
That's right.
Not the F.
That's right. It is the F block.
So it would be 6F, or I don't like up an N number.
Yeah, the N value. Good question. Well, the L value. Do you know the L value for that F block?
No.
What's the L value that corresponds to F?
6?
No, that corresponds to F.
Oh. Let me see. It's 3?
Is it 3?
3. That's right. Good. So remember this. What do we got? We got L. equals, I cannot draw nearly as good as you can, equals 0, 1, right? So this is S, P, D, and F. So if L equals 3, right? If L equals 3, then what is what's the first n value for L equals 3? What's the lowest possible n value for L equals 3? Can you guys work backwards like that in your minds? If n equals 3, can L equal 3?
No.
No.
It would be 2, right?
L would have to be 2 if n equals 3. So if we do have L equal to 3, what is that n? What can n equal?
4.
That's right. So n has to be 4. So the first L equals 3 is n equals 4. Okay, so that's 4F. And then we have to make sure we have enough electrons in there. How many do we put into the F block? Or F subshell? 4F, how many?
15.
Okay, it's actually 14. 14. Now, the way our periodic table has it, it's brought down lanthanum and actinium from that D block and kind of led the F14 block for it, or the F block for us. But there's only 14. The lanthanum and the actinide are still in the D block.
Okay, so then there's 7 subshells if you were to like draw it out.
That's right. That's right. 7 subshells, or 7 orbitals within that 4F subshell. So 4F, 14. And then after we're done filling up the 4F, what do we got?
Be the D block.
Yeah, then we're in the D block. So we got to go across the D block all the way. 5D, that is still 10, right?
Yeah.
5D, 10, and then what?
6P1.
Very good, 6P1. Excellent, let's go back and see if anybody else got it right, okay? Okay, so hopefully you guys recognize that for thallium, we need to pass through we start with xenon, our core here, and then we have to go 6s2, and then we had to pass through the F. Now, maybe some of you were struggling trying to determine, should this be a 5F, a 6F, what should it be? Well, it's the first F, right? It's the first time we've introduced F, and also on the periodic table, it's the first time F electrons are on atoms, right? So the L value that corresponds to this F, anybody know what's the L value that corresponds to our F block? 3. The L value is 3. So for the first N value, if L equals 3, the possible N value, the lowest, would have to be 4. So that's how we can remember it's 4F. Another way to remember it is just that if you're in the D block, we've already talked about how you decrease the N value by 1. If you're in the F block, you can just remember that you have to decrease the N value by 2. How many M sub L values are going to be possible if you have L equal 3? What are my possible M sub L values?
3, -2, -1, 0, 1, 2, 3.
That's right. 0, 1, 2, and 3. So now what does that tell us, or why is that helpful? Well, what that shows us is the number of our orbitals that are going to be in this 4f subshell, right? So that tells us also that there must be 14 electrons, because we have 7 different subshell, 14 electrons. Okay, so we just went across this subshell there, and now we have to go across from here to there. Oh, I should note that this periodic table, and different periodic tables do it differently, but the one that we've been using here, it takes lanthanum and actinium and removes them from the D section here and puts them down here to kind of lead into the F. So really this is the F block, and these two belong right there. Okay? So after we get to 71, we can start up with 72 here, or actually this 57 and the 72 all the way to 80, and that gives us we're right here. This is row 6, 1, 2, 3, 4, 5, 6, and equals 6 for here, but for this D area it would be 5. So we have 5D10, and then when we get to the end, 5D10, we just need one more. What would that last one be?
6p1.
6p1. All right, great. Did you guys get to identify how many valence electrons then are there? How many valence electrons?
3.
3, that's right. We look at the ones that have the highest n value, and we identify the sum of those, so that's 3 valence electrons. All right, and then if we wanted to make some predictions, and again, these aren't always right, but this is these are the tools that we use to make some predictions about how thallium, the kinds of ions that thallium would form, right? What we would do is we'd think about our orbital diagram. Think about our orbital diagram. So if I'm going to draw an orbital diagram here, we're energy, and we have xenon core, and then after our xenon core, 6s2, 4f14, 5d10, and then 6p1. Okay, excellent. So, what kind of chemistry do you think thallium would like to do by inspecting this orbital diagram? Any ideas?
A +1.
That's right. That's very good reasoning, right? +1. By getting rid of this highest energy electron there, it can form a +1 ion. Okay? So we've found stability by emptying a subshell. Okay, good. The next thing that we could do,
6s and get +3.
yeah, +3 by emptying this portion down here. Very good. So the electron configuration for the thallium +3 ion would be the xenon, 4f14, and 5d10. Okay, good job. Now, somebody might have predicted that you just lose one here and form a +2 ion, and that's a possibility as well. Okay? But these are the tools that we use. The electron configuration and the orbital diagram are the tools we use to predict how elements are going to find stability. And if you look at the elements that we're typically used to thinking about, usually our conversations are about something like sodium or potassium or chlorine or oxygen. The electron configurations and the orbital diagrams also help us with these, right? For sodium, we can see that sodium has 1 valence electrons. Can you see that in your mind, the orbital diagram? We'd have a neon core and then 1 3s electron here, right? So losing that 1 electron would give it a stable electron configuration like neon gas. Chlorine, we'd have a neon core and 1, 2, 3, 4, so 2 electrons in a 3s2, and 1, 2, 3, 4, 5 electrons in a 3p, right? So I'm going to draw that out. 5 electrons in a 3p. And we can see that chlorine, to find stability, just needs to fill that 1 extra electron. All right? Excellent. What do you guys think?
That'd be a -1 charge, though.
Say that again?
That'd be a -1 charge.
That's right. Chlorine gaining that electron would form a -1, which is what we already knew. You know, I was telling you before that everything here likes to form a plus or a -1 charge, right? Like to form a -1 charge, and the rationale was essentially if they get 1 more electron, they're like a noble gas electron configuration, and that still fits with what we've added on to our understanding. So our additional understanding still allows us to predict ions for our representative elements, but now we have the ability to predict ions for a larger realm as well, or at least understand the chemistry after we've seen it.
Dr. Scott,
Yes.
I had a question on the electron configuration of hafnium-72.
Yeah.
Because you said lanthanum and the one below that, those are considered D block.
Well, yeah. This class doesn't get into this little caveat, this little exception, but this is what happens when the electrons fill. And we don't have a really good explanation for why this is the case. We don't have a model that really takes care of this very well. Whenever anybody asks, we just punish them and then tell them to not ask again. But no, just kidding. But we just say that lanthanum is lower in energy, so it fills first, but it's higher in energy after you fill here, so it comes out last. But here we'll talk about that. So, for example, if I want to write the electron configuration for hafnium, okay, the electron configuration for hafnium, I go back to xenon, and then I fill 6s, right? 1, 2, 3, 4, 5, 6. 6s2. And then what I would expect is to say 3, 4, 5, 5d2, maybe. But what actually happens is, sorry, 4f14 and then 5d2. But what actually happens is you get a 5d1 with the lanthanum first, and then you get 4f14, and then you would get a second 5d, so 5d1 for the hafnium there, and so it ends up being a 5d2, where your lanthanum fills before the 4f14, and then the hafnium fills a second electron there. Okay? And that's just an exception, and we won't have any questions on that sort of thing. So you'll never have questions about, you might have questions in the book because they might try to introduce you to the caveats a little bit, but you won't have questions like that on your exam.
Okay, thank you.
All right, so what have we got? We've got this tool, right, that's going to help us understand and predict electron configurations. Now, another thing that I should review really quick. Let's look at this one here. How many unpaired electrons does, for example, copper have? Unpaired electrons. All right. Now, do you guys? I think I mentioned unpaired electrons last time, but we have to be able to understand what that means. Unpaired electrons. Does anybody remember how many unpaired electrons would an atom of copper have?
one unpaired electron.
One unpaired electron. Okay, so how do we do that? Well, we have to look at the electron configuration. So the electron configuration for copper, going to start with an argon atom. 4s2, 3d9. All right. If we think about our electron configuration, and specifically all I'm really interested in is that 3d orbital, right? And then filling it up with 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is our unpaired electron. Now, do you guys remember I told you last class why unpaired electrons, people are interested in those? I think I told you last class. Does anybody remember what they relate to? That's right. Magnetism. So the more unpaired electrons, the more magnetically susceptible they are. Okay? Very good. So understanding the number of unpaired electrons. All right, let's see here. Wait a second. What happened? Oh, that's interesting. Okay, here we go. So we got all this done. We're good at that now. Valence electrons, I think we're good at. We can review pseudovalence electrons, right? How many pseudovalence electrons does an atom of copper have? Pseudovalence electrons.
9.
9 pseudovalence electrons. Very good. They're electrons that aren't in the core, but are not the highest energy, the highest n value electrons. Okay. So let's see what else we got. Let's talk about for a little bit now what these orbitals kind of are. Okay, what these orbitals are in terms of electrons, because we've kind of moved from thinking them as particles to thinking them as spaces of electromagnetic energy, or three-dimensional waves. Now, a three-dimensional wave might be hard for us to put our mind around, but we try to give ourselves some images that help us. One thing that we can think of is if we're detecting an electron as a particle, then you can think of this plot, this three-dimensional wave here, as an S or orbital here, right, as kind of a probability map of where you would find the electron if you were to detect it as a particle at any one given point. Okay, so this electron density idea becomes helpful not just for atoms, but for forming or talking about molecules as well. S orbitals, spherical orbitals, are, again, waves, but they have nodes. Do you remember when we talked about the jump rope? If one person here holds a jump rope and the other person holds it here, and then they swing the jump rope, they can get the jump rope, if they swing it fast enough, to go like that, obviously, but if they keep swinging it faster, they can get it to form that sort of a pattern, right? Do you remember that video? You can also get it to form this sort of a pattern as well, depending on how much energy you put in. And the regions, let me draw this pattern again down below here. So if these are two spots where people are holding the jump rope there, and that's no good. Try again. Here we go. Spot there, spot there. There we go. The regions here where there's no movement are called nodes. All right, nodes. And just like we have nodes in kind of a two-dimensional wave of a jump rope, we have nodes also in these three-dimensional orbitals. So this is our S1, S2, and our 1s, our 2s, and our 3s orbitals, and you can see how there are nodes, regions of no electron density. And that doesn't bother us anymore because the electrons aren't a particle, they are a wave of electromagnetic energy. Did I show you guys this video here? Anybody remember this video?
Yes, you showed it to us.
Okay, excellent. So let's just skip forward a little bit here and remind us that when this, oh, horrible noise. So this is a speaker vibrating in a two-dimensional, right, 2 dimensions, and we can see the nodes represented by where the salt kind of lands. And it's interesting to see what a two-dimensional wave looks like. So that's fun. But again, these three-dimensional waves are spherical, are moving not just in 2 dimensions, in 3 dimensions. The S orbitals are spherical. Our p orbitals, this is an example of an electron density map for p orbitals with nodes or regions of where electron is not. This is how I've been introducing to you to sketch our p orbitals. The p orbitals are labeled px, py, or pz based on the axis that they're on. And then these are our orbitals, our d orbitals. Now, I'm not sure if I introduced these d orbitals to you correctly. I think that I might have made you lead you to believe that they were just p-shaped, whereas they are p-shaped, but there's multiple lobes. There's more than just the 2 lobes of a p shape. So here we have the different d orbitals. This is called dxy. This is the dxz, the dyz, the dx squared minus y squared, and the dz squared. So these are the different shapes of our d orbitals. Okay? So let me see here if I can open up this let's see, what computer am I on? Yeah, this one should have it here. So as I was saying, my old computer just wasn't handling these online classes very well, so I got this new computer, but they aren't quite done hooking it up. They thought they would be done on time, but we weren't quite there. So let's look at this kind of visualization that I made. This is a 1s orbital, you can think of it. And you can think about an electron moving around there. I put that in there to help you remember that this is a 1s orbital. There's 2 electrons that reside in every orbital, so now our 1s orbital has 2 electrons. If we want to put a 3rd electron in, though, it has to go into a 2s orbital. So to go into the 2s orbital, we have to bring in our second shell. And the second shell contains 2s and 2p electrons. So if I put an electron into the 2s orbital and it goes zooming around, put another electron into the 2s orbital here and have it go around in its space, right? The next 6 electrons, one is going to go into, did I put it in? There it is right there. It's going to go into a p orbital. It doesn't matter if it goes into the px, py, or pz. In fact, you know, atoms aren't holding still like this. They're tumbling as well. The nucleus and all these orbitals are tumbling. And you can think of it kind of as a fan, right? A fan has blades, but as it's spinning, it's essentially a disc. So anytime you were to bring your finger close to the fan, even if you were bringing it close to a place where there wasn't the blade, you would eventually get hit because the blade is spinning. Same thing with this atom. This thing would be spinning, and so if you were to look at it from a distance, it would always look spherical. And if you were to reach your fingers in and touch this spinning atom, the first thing you would hit would be these 2p orbitals, right? So I'm going to fill it up, put in 6 electrons into our 2p. So now we have electrons in all of these orbitals. So I'm going to shrink it down here, bring in my 2s and 2p orbitals, my second shell, fill it up like I had it, and then I'm going to bring in my 3rd shell. The 3rd shell has, again, 3s and 3p, larger, but now it is including these 3d orbitals as well. All right, so that's a little bit of a visualization. Again, anytime you're going to actually do any sort of work to kind of think about this atom moving around, the atom will be spherical. Sometimes atoms that are rigidly maintained will actually expose these characters, these different extensions of electron density in their p and d orbitals. And that's very interesting, and we'll talk about that in some when we begin to talk about how atoms bond from one to another. Okay, so then let's go back to our oh, well, it looks like we're out of time. So next time we'll start talking about how this information also, along with giving us predictions of how elements can find stability, also tells us about the size of the atoms and how much energy is required to remove electrons from those atoms. But we'll do that next class. Anybody have any questions? Okay, if there is no questions, then we will see you guys on... You have a question, Katie? What's that? Sorry, I don't know. I had the sound turned down a little bit. Do you have a question?
Oh, yeah. This is actually a personal question. Friday, I'm going home,
Okay.
and I was wondering if it's possible for me to get like a recording of the lesson you'll be doing on Friday.
Yeah, I've been trying to put the recordings on the Canvas page. So let's see. Here, if you go to the Canvas page home, then we've had a little bit of challenges with recordings for a variety of reasons, mainly because I'm trying to get this new computer. And one of the reasons I'm trying to get the new computer is because I had a USB port that wasn't very stable. So we've had a little bit of problems. But videos of lectures right here is where... Oh, can you see my thing? You don't see my screen?
No.
Okay.
I can only see the...
Okay, let's bring it back up again here for a second.
Yeah, I can see it now.
Okay. So here on the home page, we have a link down here to videos of lectures. Videos of lectures are ordered by chapter. So you can look here at chapter 1, right? We're in chapter 8, so you can move down to chapter 8. And these are various lectures over, well, with a couple of years now. So this is kind of last year's lecture, chapter 8. And then here is our most recent lectures of chapter 8. And so hopefully this new one will be able to go right in here. That make sense?
Yeah.
Okay. Any other questions? Yep, you bet. Katie, Samantha, Kim, any questions? Okay. We'll see you guys later then.